My name is Nicola Menet, and I'm here with Alexander Terzic. We're excited to introduce a novel state space model designed for state tracking. To start, Alexander will familiarize you with the problem setting.
So in this work, we are dealing with selective state space models. Introduced in 2024 in the Mamba architecture, selective state space models process sequential data using a linear recurrent system. And in this system, crucially, the transition matrix A is a function of the input. Such models have become an attractive alternative to the transformer due to their high performance and constant memory and time inference cost. However, both the transformer and Mamba, they're limited in their ability to execute simple algorithmic procedures. In particular, they fail to accurately model finite state automata. So in this particular setting, given the simple parity automaton, we train the models on sequences of certain length and then test them on longer sequences, and both the transformer and Mamba exhibit failure. There has been significant effort to increase the expressiveness of state space models, focusing on the structure of the transition matrix A. However, none of the previously proposed structures managed to offer optimal guarantees. They either require a large model or are computationally inefficient. We propose a state space model based on structured sparse transition matrices that offers better guarantees.
To understand how we enable finite state automaton emulation in state space models, consider the example in the slides. We represent the states x, y, z with standard basis vectors and a state transition through a matrix operation that inherits the sparsity from the state representation. Note that the state transition matrix has column 1 hot entries corresponding to the target state. While the sparse matrix representation is technically sufficient to ensure emulation of finite state automata, it requires the hidden dimension to scale with the number of states. In contrast, an often occurring class of finite state automaton, the modular counters, can be represented in state space models much more efficiently via complex scalars on the unit circle. Our model architecture, called PDSSM, incorporates an inductive bias for both representations of finite state automata. Through a diagonal matrix generator, here in blue, modular counters can be efficiently represented. Through a one-hot binary matrix generator, here in orange, more involved state transitions can still be modeled. Multiplying the column 1 hot binary matrix with the complex diagonal matrix results in a structured sparse transition matrix that is column 1 hot with complex entries. This PD parameterization is closed under matrix multiplication, and the multiplication scales linearly in the hidden dimension. Together, these two properties enable parallelizable efficient training, for instance via parallel scans. Moreover, the resulting state space model is bounded input, bounded output stable, and it can represent any n-state finite state automaton using a single layer with hidden dimension n. This representation is optimal. The hidden dimension cannot be reduced in general. Next, Alexander will present some exciting empirical results.
So firstly, we have runtime measurements, and here we are comparing the PDSSM with a diagonal state space model and a dense, unstructured state space model. We can see that PDSSM incurs a constant factor overhead compared to the diagonal model, whereas the unstructured one incurs an increasing overhead with increased hidden dimension. On a range of finite state machine emulation tasks, PDSSM exhibits almost perfect accuracy, significantly outperforming all related methods. In a more natural setting, with long sequence time series, our model is within standard error of the state-of-the-art, demonstrating its applicability on tasks beyond finite state machines. On further longer sequence tasks, our method exhibits significantly better accuracy compared to Mamba, and we further introduce a state tracking task in which transitions are encoded as sentences in English, and our method again significantly outperforms diagonal SSM baselines.
To summarize, we propose PDSSM, a novel SSM optimized for state tracking. Theoretically, we prove that it achieves universal finite state automaton emulation with the least possible hidden dimension. Empirically, we demonstrate that the model learns to track the states of complex automata. We furthermore test our model on long-range time series classification and observe state-of-the-art performance.